Right, so looking at going into sheet metal, this is going to operate out of the parts module. So any of our part inch, part millimeter that we're interested in working from. And we'll start off with a basic box. So some of the things, we have the blocks from last time. I'm going to go ahead and turn that off as a toolbar. I want the sheet metal to show up in the Command Manager tabs. Otherwise, if I don't have it in the tabs, I have to go insert sheet metal and then pick my whatevers, my features, my commands out of that pull down. To get the sheet metal into the tabs, you right click and we're going to hit the checkbox next to sheet metal, and that will switch us over to all of those commands showing up on the Command Manager. All right, so that gets us started. A couple of things that when we tell that that we're going to create a sheet metal part. So let's go into the sketch, and we'll first talk about the two basic methods to get started and advantages to either one. All right, so if I go into the sketch, I'm going to go with a let's go to the top view, open up the sketch. I'll go to a center rectangle. And this enclosed closed region is going to be fine. We'll do 4 by 2. And when I go back over to sheet metal, and just kind of like surfacing and kind of like some of the other things, is your tendency is you're so trained or ingrained to go to features that you have to kind of make that right turn and go to sheet metal. So go to sheet metal, and there are ways of converting. There are ways of pulling some of that geometry off of solids, but when you think in terms of sheet metal and staying in sheet metal, we want to be jumping into that tab. All right, so telling it that this is a base flange tab, the first item is going to be a feature placeholder that retains this information. So we can mix as a multi-body part. We can mix weldments, we can mix sheet metal, we can mix into regular extrusions and geometry. Do we really want to? Probably not. It's, you know, as far as the strategy, but if I needed something for reference, small part or mixing in the weldments and the sheet metal, as long as it wasn't overly complex, I could manage it. All right, so we have to decide. So just like the weldments is going to produce a weldments placeholder, sheet metal is going to produce a sheet metal placeholder, and it's going to retain this information. Sheet metal parameters are 0.25, quarter inch. I want a 10 gauge aluminum, so let's call it 130. And be aware that when you go to the gauge tables for aluminum, steel, and stainless steel, there are minor variations in the gauge sizes. So verify. Check it and make sure that you know, and within the tolerance zone, it's probably okay most of the time. But getting into finer, you know, trying to hold the precision detail, 10 thousandths is going to affect the overall or your overall dimensions. All right, so the reverse direction, does it go up or go down? We'll let it go up. And then we get to the K factor, and my K factor is about shown as 0.3. The default is 0.5. What the K factor says, and I need to make up a little graphic for this on the video, is that in our material, when the material is in its free state, some thickness, the forces, the internal stresses, and not even so much the arrows going that direction, but okay, arrows going in both directions. This is my K factor, the equalization of the stresses inside of the material. As soon as I put a bend on that material, as the outside goes into tension, we're pulling it apart, and the inside goes into compression, we're crushing it, that K factor is shifting by some percentage. It's no longer halfway. And the steel, we found it to be about 0.25 to about 0.3. So that's why we end up with, that's why my K factor was set at 0.3. All right, so ideally, as we increase the stresses on this side, increase, and pretty much are pulling everything the opposite way on the outside, we're going to take those forces into account because that is deforming the material. When it's in its free state and we fold it, it's going to grow, or it's going to shrink as depending on which way we're pushing or pulling, so to speak. All right, so we want to take that into account. Yep.
So it's 0.5 or less?
Typically, yeah. 0.5 is a good guess. Now, we're going to look at the other bend allowance settings. But you think about just a piece of material sitting there on the table, whatever the internal stresses are this way are going to be the same this way. It's when we make that bend and this radius grows, and this one went very tight, that we've upset that that balance.
So if it's in free state, would that be a K factor of 0?
Well, 0.5. It's halfway. We're not shifting it up. We're not shifting it down. You really wouldn't go to the way that I understand it. Now, that's a good question because I haven't ever asked it before, I guess, is what happens when you're above 0.5? Is you're shifting it to the outside, which most materials, ductile or not, are not going to shift to the tension side. The shift is to the compression side. So when we say we've taken a percentage and moved it towards the compression side, that is, there is more stress on that side than the other. There's more internal stresses being located or being centralized at that on the compression side. All right, that one's hard to visualize. I'm going to have to go back, and now I have something to do homework on, because now I got to think about what's actually happening there. All right, so on the other side of things, we have the bend table. We have bend allowances, bend deductions, and bend calculations. Each of those is going to be a table that are going to go to actual. We took a piece of material, went out and bent it, measured it, got the variation in the initial length to what the bent length was, and we built that into the table for various thickness on the material. Ran samples and got usable data out of the mix. All right, so on my side, I don't do enough sheet metal to get to this level of detail. All right, so if you have or you do a search for these tables, they're certainly going to be more accurate than what we're doing with the K factor. The other thing is, if I'm sending this out to a sheet metal shop, then really what I'm interested in is, hey, if I send you this geometry and I have a K factor of about 0.3, you can send me the quote, send me the estimate based on material sizes and bends and everything else. And then when you get it, you build in your bend table, you build in your bend allowances, and can make it. I'm good with that. I don't need to that nth degree on my design side. All right.
If we assign the materials to it, will that affect any of that?
No, not so much. It's just a calculation based on thickness. It doesn't take into account the ductility of aluminum versus steel or any of that that I know of. It is pretty much just saying this is 0.13 thick, and when it calculates for how much the material needs to grow or shrink, for a 4x2 piece, we're only going to see thousandths. We're only, if we see 10 thousandths, I'd be surprised. But how much sheet metal is, we're stamping out small pieces, so it's almost negligible at this size. What happens when we take a piece of 60 by 120, 10 gauge, and do whatever laser pattern or whatever plasma pattern, and then take it over and start bending it up over feet, not inches. then that growth, that everything becomes a lot more apparent. And as you get into thicker materials, definitely so. All right, so we're gonna see 4x2. We'll go through the process and see what it comes up with actual measurements. So at 2 decimal places, I wouldn't expect to see a lot of variation. Auto reliefs are rectangular tears or oblongs. This is when we bring up a corner, or I bring a flange at the middle of the part. How is it going to interact at that level? For little boxes, everything was to the outside, so it's not an issue. But what happens if I have something internal versus external? And then the ratio is the depth of the tear or the oblong in relation to the material, so you don't get the types of deformation. Okay, so we go ahead and accept. There is my sheet metal and the sheet metal definition. There is my base flange. And the flat pattern, well, everything's a flat pattern right now. We haven't folded or unfolded anything at this stage. All right, so we're not concerned about the flat pattern, but the flat pattern is in suppression because when we either hit the button or unsuppress, then it's going to flatten. And my tendency is to want to use the fold and unfold, but those are different monsters. Those have different kind of different functionality. And typically there will only be one unfold and one fold in most cases. All right, so we try to build that in. So we'll take a look at those coming up. But keep in mind that the unfold fold is not the same as the flatten. The flat pattern is what we're looking for detail, or what we're looking for in the drawing. All right, this also generates a cut list. So if I had multi-bodies, this would generate its own set of properties. And the properties are kind of weird. They're not really that easy to get to and decipher. We do want to update automatically since I'm here. I'll let that go. And maybe I don't have enough in there. I'm not seeing the properties now. Go down one more level to the base flange. There we go, body properties. Nope, still not it. Well, maybe I'm thinking of the weldments then.
Yeah, why would they have a cut list in a sheet metal part?
Well, everything's a cut list.
Oh. Oh.
I think we need more geometry. We're gonna have to come back to that one because we need more geometry first. All right, so to add the vertical walls to our box, I can go around the outside, and we could select the chain, or we could select whatever. And these are going to be then edge flanges. All right, so when I pick an edge flange, it's going to allow me to pull that geometry up. All right, these do not all have to be the same height, but of course it's going to be the same material. And to a certain extent, let's see, we have a default bend radius that was back in the other segment. Default gap distance between the edges. And let's see, 90-degree angle, blinding condition of 1 inch. And that will set the location, or set our basic parameters. Well, the 1/4 inch for something this size is a little on the high side, so I can uncheck the use default radius. But if I set up a die, if I set up for the finger break, if I set up for whatever, I'm not going, unless I have to, I'm not going to change those dies out. And I want to bend everything with the same default radius. So we'll come back. We won't override that setting. We'll go back to its initial setting in the sheet metal feature. All right. Outer dimension to the outer virtual sharp, so where the radius, where the two walls come together without the radius. Going to, let's see if we can see that better. All right, so the first one, a little bit shorter, a little bit taller, a little bit shorter again. So depending on the bend, the over bend, tangent, and inner virtual sharps versus outer virtual sharps. So just where do you want to pull the dimension from? And then the flange positions, material inside. So the box stays 2x4. Everything gets sucked in, and that base gets a little bit smaller. What was that one? Material outside. The bend outside, so the 2x4, and then go into the bend, adding the radius to it. Let's see, bend from the virtual sharp. So as these angle changes, the virtual sharp kind of moves a little bit on the sine, cosine, tangent, the whole trig calculation. And last one, tangent to bend. So those two should be pretty much the same. So we just have to make a decision. Do I want to have the material outside and the radius stays in, or is everything bent inside? So let's stay with the 2x4 bent inside. If we trim the side bends, nothing really there to work from. Let's see, on the offsets, we go to another offset and can adjust the position. I don't really want to do that just yet, so we'll turn that one back off. And then custom bend allowance, custom relief type for this particular feature. All right, so I'm going to go ahead and accept that, and we'll come back into it and after we take a look at the feature. So rather than setting that local parameter for the bend radius, I'm going to go back into the sheet metal, and we'll say that that is a 60 thousandths as opposed to a quarter of an inch. All right, so where I was focused on the K factor, we had the material, we have the default bend radius, and can go ahead and accept.
Where'd you go?
We went back to the sheet metal feature, the very top thing, the placeholder that it put in when we started the sheet metal. And then you right click on it and edit the feature just like any other, and we can set these as global variables or as global parameters is a better term. Our global parameters for this sheet metal part. All right, so I don't need to do anything to the base flange. When I look at the edge flange, I have 4 undefined sketches. I have 4 edge bends. All right, so that's how it's managing the geometry. We can edit these individually, but don't recommend it. We'll go back in and edit the feature, because under the edge flange 1, if I edit flange profile, I do not have to take this all the way across. This is a kind of like a converted sketch. Let me go ahead and put a dimension, and 0.87 is okay because it takes into account the 0.13. But the thing to watch for is I only need, well, let's see which one it is. I only need part of this wall. I can reduce that wall by X amount. So let's select the midpoint, and we'll set this with symmetry to the midpoint. And it's flashing up the previews. And this profile sketch window that tells you that editing, that has been around forever, and it has always taken up more of the screen than it needs to. But if it didn't take up that much of the screen, you'd probably never see it and not know to go back or to tell it to finish. All right, so we're 4 inches. I want to be 2 inches off the midpoint. That fully defines that sketch. I can go back, and that flange gets smaller, and because it's an interior, this is my obround or my tear. That's my relief type. Because otherwise, I bend this up on an internal like that, and this is going to deform all of that material up into that radius. So we have to have some mechanism to allow for that bend without interfering with the material to the side of it. All right, so if I go to edge flange 2 and decide that that wall needs to be 0.75, I can adjust it. That one's going to have a little bit, wires are going to come out underneath it, or when we put the outside flanges on it to bolt it down, there's going to be some clearance for it to sit over a plate, whatever. All right, same thing. I grab this bottom point or points, and those are movable. And 3, I want 3 to be the same as 4. Well, I can't really do that from here, or can I? Nope, I can't expand that back out. So one of the things that by preference, oh, there it is. Never mind. Let's see. We want this to be the same height. So I can't make that coincidence so much. But let's see if we go the other route, and I said that those two from the edge flange 1 sketch, and then control select the sketch that I'm actually, the flange that I'm actually editing, I can set those to equal. So if this one grows, this one grows. And then go back, and edge 4, and let's see, oh, edit flange, and this one can be set to equal. All right, when I go back, I'm just going to look down through my properties, and now notice that the flange length, that distance, it went away. We're controlling it inside of the sketches as opposed to at the feature level. The other thing is all my sketches will be fully defined. So it's not necessarily a bad thing that we ended up with the dimension and it's controlling, they're all the same height. There's no issues with these being partials, that type of thing. Then I go over to the side that says I don't want to do 4 separate items. I don't want to control these that individually. I'm going to build this edge flange to go around, but then editing the flange profile gives me that control over just that side of the box. All right, so that gives us our shot. All right, so the difference would be then going back one more time, and now that we have the relief, I go to the outside, the relief gets smaller. I go to outside the bend, it goes away entirely. Shouldn't see too much in the way of the tangency. They just kind of jump back. Okay, so let's where I can get away with it, bend to the outside. That's my preference. You know, in some condition like this, I would shrink this so we have a 0.13 radius with the 0.13 or 0.06 radius with a 0.13. I would go into that base flange sketch and make it 0.38 smaller. If I'm doing the math right, I would make it smaller so that I would end up with the outside of the box 2x4. So I'm not doing that calculation or driving some of that internal geometry staying to the outside. Right? But it's a matter of what equipment you have available. The standard finger brake has a lot of capabilities, but you're going to pretty much a sharp edge. It's not like the multi-ton brake press where you have different dies, you have different radiuses, you have different geometries that you can get into this into these corners. All right, so let's go ahead and save this.
It doesn't like the contours and regions.
It's not a contour and region type deal, no. So if we need holes, if we need additional geometries in this sheet metal box, we're going to do it as separate features. We're not going to include it in the flange or in any of the specific commands. So this is my 2x4 by 10 gauge box. Hey, I think I'm giving you guys way too many boxes, so we need to do something different than a box. I made it way too simple. No. All right. And certainly this is just our quick intro, kind of getting through the process, creating the base flange, creating the edge flange as this bottom geometry.
Does it matter which edge? Like we pick
The bottom edge?
Yeah.
No, it really shouldn't. I mean, it's it's going to bend from here to here and from here to here. So I think of it in terms as the bottom edge, or that's my preference to select. So I kind of do it consistently. I guess but you should be able to pick either one to make the to put the flanges in. All right, so I want our new drawing, and this is where prior to, oh geez, when did they upgrade that? Probably 2000, somewhere between 2010 2012. Sheet metal got a facelift, and one of the things was how they managed the suppression of that flat pattern. All right, so I put this in, and I'm not even worried about telling it to go to the flat pattern inside of the part. It's the drawing that's going to create a derived configuration and will ultimately, in my opinion, ultimately manage my sheet metal part. So we go in, grab the flat pattern, and place it. It puts in the downs, it puts in the bend lines, it puts in all of that basic geometry. Okay, what that does when I save this, and we'll go ahead and save it as the drawing file too, is I go right back to the part and go to the configurations. Now I have default sheet metal, flat pattern, blah, blah, blah. When I click on that, now I see the sheet metal, I see the envelope, I see the bends. All right, go back in here, and let's see if we go to, let's just go to flatten. Flatten, I get the same thing for the most part, but if I had, well, we'll do that on the next one. If I do that on the, before I go to the sheet metal, it is at that process that it makes that derived configuration. That is really what I want. I mean, I can look at this, the flat pattern, and go back and forth, but without that derived configuration, the drawing isn't near as functional. So I'm searching for terms there of to kind of put it in context, but when you see it, I guess when you see it, you'll know it kind of thing. So those are able to move, and each of those can have leaders. So we'll go over to set it to a leader. All right, as opposed to everything sitting on top of the part. My favorite quote from our brake press operator is, "My brake press only bends up." So all of these downs are no good to me. All right, so that being the case, can't really rotate or to convert it. I'm sorry, we can rotate the view to make it lay a little bit easier along the side, and then adjust our positions accordingly. But really, where we got into trouble most of the time is when we had Z bars, that one had to go up and one had to go down, and the distances were different, and which one was the up Z and which one was the down Z. Okay. So now that I have the flat pattern in, we can go back and under the view, grab the front. We'll go ahead into the projection, the top, the right, the isometric view. They don't necessarily have, oh, got an extra one there. Don't necessarily have to be on the same sheet, so we could open up another sheet to place this. And set up for our dimensions. Oh, okay. And then let's see, what were the, I didn't quite run into that too much, but we can dimension to the bend lines. All right, as well as to the overall size of the stock.
So if I get the flat pattern, it's not showing me the bend lines and stuff?
Then did you take it into the drawing?
Yeah.
And do the, It should. I don't. The bin line should come in automatically. Yeah.
Okay.
All right. So we'll go ahead and save that one. All right. So to see where the bend is for that relief, for that corner relief, because we come back over here and kind of how it's calculated. As those get closer together, it will change the relief geometry in the corners, and then we can also change for overlaps or for the gap. Okay. So that'll just be our first quickie example. Strategy 2, and again, it's just what is your direction on the geometry? What can you get the most bang out of the buck for? All right. So if I go into the front this time, and I'm going to set just a profile, and let's just say this has one 90 degree and one 45 degree. And those are going to end up being at the same height, and we'll make those horizontal. Nope, didn't quite want that dimension. So 2.5 is okay, 4 on the base, 5 on the base, 45 degrees, and whatever the length comes out. All right, so that profile will generate valid geometry, but it's also going to give me my 2 initial bends. All right, so we were 4 by 2. Let's stay with the by 2 sort of. So sheet metal, base flange, and we're pulling in or out. Okay, so 0.13 was our setting. 0.06 is the bend radius, and we are to the interior of our dimension. Right, so the sheet metal has been loaded to the inside. If I reverse the direction, it's loaded to the outside. You have to watch that because that's going to make you grow or shrink, obviously make you grow or shrink, depending on what your desired result really is. So let's stay to the inside, and we expand out direction 1. We'll go to 3 inches, and that sets up the initial. All right, so I have my first bends. Let's go ahead and flatten, and the flatten will show you in the background, but there's no default sheet metal flatten whatever prepared for the drawing, which is really what I need. So at this point, I can look at it, but it's not really doing anything for me. Oh, well, we were going to check. So I made. Let's take that off. Well, if we were, and this is probably a really bad example, but oh, we didn't measure. I didn't measure that line. So let's show that sketch. So 3.54, 8.54, and 2.5. What's that? About 11.04, something like that. There I go doing math in my head again. And we go to the flatten, and I go across that edge, 10.73. All right, number that I just roughly added in my head is a 1/4 inch longer. That's the going through a 60 thousandths bend. That's the deformation in the metal. We know that it happens, exists. We just don't know much to what degree and how much based on the material. So that guess of 0.3 is how much this is going to shorten, so that as it deforms going through those bends on this thickness of material, what does it need to be to end up at that finished length? All right, so I didn't take into account the radius. I didn't take into account some of the other, some of the other possible dimensions that we would need in there. But if I just added up those linear dimensions, I'm quite a bit over. All right, so we'll get out of the flatten. That puts us back into our bend length.
patterns that I've seen are just for reference only. I guess the reasoning is that whoever makes this will have their own calculations.
Well, yeah, and are you, so, starting back at the beginning of the design for manufacturer conversation is, what equipment do we have available? How experienced are the people, the operators, the people that are making the part? Where this shifts is, are we putting this on a punch machine to stamp it out? Are we putting it on a laser? Are we putting it on a plasma? What are the variations in the tolerances? For reference, there's a certain amount of tolerance. Sheet metal is, there's a reason that sheet metal is maybe at a minimum a 30 plus or minus a 32nd, is because hitting those numbers over and over again is difficult, to say the least. I think the standard tolerance is plus or minus a 16th, kind of like the woodworking is. You have plenty. We're going to let it shrink or grow an eighth of an inch overall in the worst case. So to say that it's for reference, no, I'm going to hold you to those tolerances. That when we go out to like I said, laser, water jet, plasma, whatever the process is, and it's a reasonable tolerance. There may be some stack up, but it's within 15 or 20 thousandths coming off the machine. You should be able to bend it within another 15 or 20 and stay within my plus or minus the 32nd. So on an inspection document, when it's bent up, yes, the finished dimensions are the critical dimensions, but realistically, if you come back and say, well, I bent everything at an inch when it was showing up at 7/8, and you didn't make the part, or the part didn't meet that final inspection, it's not really, it wasn't a suggestion that you bend at that you need to be pretty darn close to those bend references, or give me some feedback as the engineer and say, here's the variation, here's where the K factor came in, here's where the bend allowance comes, so that I can get closer to give you better numbers to set the stops, to set the brake where it needs to be to make those bends. So I can go either way on it, but the argument that if we put it out on the floor and they have something different and it is a secret and nobody else in the company is sharing it, then it's not much of an organization, not much of an engineering document to begin with. So we might as well go to Bash's and get our brown paper bag and sketch it up and say, here you go, make it however you want. And that's kind of facetious on my point, being a smartass. But really, what is the purpose of this document? Is to get us consistency, have tolerance control, and all of the parts are within a reasonable manufacturing process. So, yeah, I would. It would be a discussion. We would have a discussion of why those flat pattern dimensions are for reference only.
Yeah, I think the drawing that I'm thinking of, it had like part shall conform to final, dimensions.
The final fit dimensions, yeah.
Yeah, and then the flat pattern use reference.
Yeah, but on the other side of that, those final fit dimensions should be, are going to be open dimensions, and once it's bent, you can't control it anymore. What are you going to do? Unbend it?
Yeah, do they just make? I guess they would make one, right?
And make one and check for and that would be where you'd start to accumulate your bend allowances. And that comes back to too, is having the conversation with the sheet metal shop, with the guys, and saying, hey, what do you prefer? Just like having that conversation about maximum material condition on all those holes. If you want least material condition, I can give it to you, but that doesn't quite set in my brain, so please explain it to me. I'm just not that smart. So if you're doing something that is I would say maybe not by convention or out of commonly accepted practice, we need to know about it. So yeah, yes, we want to hit the final, but I'd almost say that the tolerances, the bend, that flat pattern, if it's an issue, that flat pattern needs to be redlined. And I bent all of these not at 0.89 but at 0.91, and I got the desired result of the outside dimensions being the same. That needs to complete the cycle, go back to engineering. Otherwise, the information goes off the waterfall, flows downstream, never to be seen again. And then next time we do it, they get the same drawing, they do the same things. Oh, the new guy's here. He does something different, it doesn't work. Why doesn't it work? He's in trouble because he bent up crap. Well, no, he didn't know that, the process is they're engineering it on the floor. All right, so if we're going to hold any, we're going to hold any of those dimensions, or hold, and really, how critical is it? We're injecting enough float into it to begin with that it should be able to meet the final OD, ID, whatever the fit dimensions are, and still have those base dimensions be able to be met. So I'm sure I'm going to get some nice comments on YouTube on that part of the discussion. And it comes back to too, I've had sheet metal guys in class that said, we do it this way, and it works for us, and that may not be the same in other shops. So, if you've been doing it for 20 years, then I'm sure you have know all the tips and tricks that the rest of us are just going, wow, it's black magic, voodoo. All right, so back into this part. Let's put some flanges on this and run through some of the other. No, we can't do a miter flange, so we'll walk that one out. Let's go with the edge flange. Well, we probably could do a miter flange, but it doesn't lend itself to this juncture. Let's put it this way. So let's bring a flange up, and we'll bring it up to the same height. Now when I edit this flange, in this case, let's go collinear to an edge. All right, so it brings it up, and now it says those will stay the same height. So I'm trying to build in enough intelligence, or enough logic anyway. I can't say intelligent, but enough logic that this will follow if I grow or shrink that flange. The other thing is, well, I don't know how well it's going to work, but let's go ahead and get rid of the vertical and tip that over. Nothing says I can't. If I can cut it, and the material that's cut does not overlap on itself to where we can't we can't actually end up with usable geometry. No, not collinear. Maybe coincident. Hey, there we go. And we'll go ahead back, and then let's put that to the outside. All right, so we end up with our gaps. Now that's not to say that this is going to be a weird bend. I look at that and go, I'm not sure I want to do that. I'd almost rather look at a stamping or a multi-hit stamp process if it's going to be. But we'll discuss weird geometries later on. All right, so that puts it in. It puts the relief. It has the gap. And based on length, well, that one grew because we were to the inside. That one probably grew a little bit. That I may have to push that back.
All the material.
Yeah. So let's see if the what do I have for measurement there? Oops. So it's showing about normal distance, about 0.13, about the thickness of the material.
Could I just run a cut through that edge?
You run a cut, but we're going to see if our direct editing, because we haven't really talked about much direct editing. Direct editing is move face, and move face is nice because it doesn't do I say really bad things. So we don't have to keep track of the cut, but it lets me push that back. So direct editing, move face, pick that in face, and then it shows up as I'm moving 0.13 and within the accuracy of our measurement. And usually the move face is adding material. When we flip the direction of the cut, it removes the material. So there's a lot of things that we're going to end up doing eventually with the direct editing. Yes?
Is it reflecting the drawing now, or the sketch?
No. The sketch is still the original sketch. All right, so whatever the calculation, all right, so we told that to be even, which is exactly what it did. But it also grew the tip. So my other choice, instead of moving the face, would have been, oh, hey, I really need to design this to the outside and make these dimensions smaller by the thickness of the material, the radius, that kind of thing. But those are decisions, you know, as we're going to have to make as we go along. At this point, I'm not that far into it that I couldn't go back to the edit flange and reverse the direction. But if I'm looking at those critical dimensions, 5, 2.5, and I just want to hold those, doing that small adjustment on the direct editing, that's not a deal killer.
How do you get to that direct edit?
If it's not on, you're going to right click in the tabs, and it's going to be a checkbox under direct editing. And probably need to mention again that you can turn these on and off. The recommendation is that do not turn all of them off. It takes a concerted effort to get one of them back on to where you can use it again. So there's something that, an enhancement request back to SOLIDWORKS that says, make one of these, pick one, and make it to where you can't turn it off. But as it is, you can turn all of them off, and then it's, wow, that's kind of a mess. All right, so the hem is a strengthening, so it folds the top edge back on itself. So we'll just take one of those and go to the hem. Again, the miter flange is kind of like when you're doing picture frames and those edges that have to come together, and where it's going to account for going up at angles over and keeping those 45s together and trying not to intersect. So the I think that one's new since the last time I've done a hem. So hems are we're gonna have to look up the machine because I think you do the hem before you do the bends, because it's folding back in on itself. It's not going to be very, very usable, but it has to roll this edge back over on itself, and it's a strengthening feature. So this one goes over, let's see, we have a length. Let's stay with the 0.13, and distance will go down to 32nd, maybe. Okay, rolled back in on itself and touching, or as an arc, and degrees and gap. So apparently I didn't leave that one big enough. 3, 0.25, no. Why no, it didn't need to be 0.3. So 0.25 or 0.13, well, maybe we need to. All right, so you can kind of see that that gap. All right, so it folds back in, and it can go either way. Do we want it to be added to the material or stay inside of the material? And relief types, K factors staying with the standard. Let's see what the hem width looks like. Well, so you can do a partial hem. We can grab that and pull it back, and it will only hem along that that base edge. Okay, so strengthening. Let's go with the jog on this side, and I believe the jog and the sketch bin need an existing. So this is going to kind of mess up, but whatever. We're going to end up there eventually anyway. So go ahead into create a sketch. Back to the sheet metal, I want to jog. The fixed face is this face. Oh. And distance, let's go 0.5. So it's putting that that step in. And do we want it to be inside, outside, or contained? So outside offset, inside offset, or the overall dimension. The jog position is bend center line. Shifting materials, and some of those results don't look like they're working, but it gives you the options to adjust. And then if we go 45 degrees and on the angle. The other side of that is fixed projection, default radius. Oh, and then change the side. So whenever I do these sheet metal demos, they always end up looking like Art Deco unless it is just a box. There you get pretty wild. What are we doing? All right, so a sketched bend. Same thing, we need a planar face. Yeah, let's make it at least interesting. All right, so bend parameters. Again, we're looking for a fixed face. What's going to stay? What's going to bend? Reverse the direction. 45 degrees. And then same things, material inside, material outside, bend outside, or just stay on center line. The cross break, I don't know that's gotten any better, but when you look at the big trays, that kind of strengthening the X in the bottom of it, that is a strengthening feature. As far as I know, all it does is draw a sketch with the cross. It doesn't actually do the deformation of the material. So we'll have to check on that one, but I don't want to spend too much time on it. Going into the corners, closing the corners, treating it as a welded corner. So closed corner is just going to extend whichever one that we choose to the overlap. And then the welded corner. Let's pick a face. Pick a face. Oh, sorry, got to go through. Add the fillet. Fillet radius of 0.1. That looks all right. Huh, interesting that it only did the partial. That it didn't come up to the edge. Well, let's see what it does. But what that's doing then is adding should be adding a body somewhere. So welded corner. Go. So it treats that just as its own little piece of geometry. So anything that is a weld bead or welded corner, whether we're doing the sheet metal or the weldments, weld beads go in at the last. Forming tool, we have a newer style underneath the design library, and we'll have to finish up on this. Let's run through this real quick. Extruded cut, simple hole, or just base geometries. Vent geometry will open up for like a fan. Let's see, unfold, fold, flatten. We need to do the rips, gap between your two edges in a sheet metal part, and then insert bends. Is if we did a thin feature or something from the solid side and needed to convert it over to sheet metal. The forming tool then is typically in the design library, forming tools. And one of the things that happened is they changed the process. So if I open up one of these countersink emboss, is this does not have the same geometry, so we pretty much have to convert this to make it functional for the sheet metal. And now I got to dust off some brain cells and remember how to do that. Let's see, sketch orientations. We got all of that. Well, let's see what it does when it drags it in. I'll show you the error first, and then we'll come back to it. So countersunk. Oh, maybe they corrected. They might have corrected it. So flip the tool. I know in 2014, 2015 that some of those tools were not defined correctly, and it would give you an error when you insert it. So no rotation, position comes in as a sketch. Wherever I put a point, I would get another one of those, kind of like the hole wizard. And that's going to be the punch tool, and a little thick for that punch tool. I think we just beat the heck out of that one. All right, so at this, so what did I put in here that I can't unfold? All right, so no, it wasn't the move face. Interesting. Oh, as soon as the welded corner went in, what do you want to bet? Okay, as soon as the welded corner, it lost the unfold fold. So another reason to put welds at the end. All right, so let's go ahead and do the unfold. You're going to do the unfold before you do the fold. So we'll do the unfold, fix face, collect all bins. All right, so this is not the same as the flat pattern because it's including the radiuses as a definition. It also didn't do the hem, which is okay. So either that or I need to do, well, typically I don't want to do secondary unfolds if I can help it. May go back, see, he's not going to let me reorder that. Nope, guess not. Can't reorder the unfold, so let's undo. And fix face, bends to unfold, collect all, accept. All right, so the purpose or reason that I want to unfold is this will give me a detail, and let's see, is it still the same length? 10.6, so there is a little bit of the variation on the unfold from the flat pattern. But this shows me the radiuses as locations instead of the center line bends. I want to say that's important. I don't have a really good example, but when we rolled the large sheets as opposed to bending, the roll locations and the radiuses of a roll. So trying to make a shell with like a 120 inch radius or something along those lines. We don't want to see those center lines. We don't want to see the bend lines. We want to see where the radius starts and ends, the length of the radius, and where we can pick up those locations. The other thing then is if I need to cross over across one of these radiuses, I can extrude cut. Well, any of the sheet metal should have length to thickness. Length to thickness is going to be a better choice than a depth. And when I go back to fold this up, anything that is in between the two, collect all bends. Now I've got the relief across the corners. Go back, shouldn't have any major. Oh, hey, nice weld. So it rebuilt nice. That is, I'm really impressed with our welder now. That guy can really weld. All right, so that's a little weird, but okay. But it's another one of those we could build that out, and again for hypothetical geometry, probably not. All right, so flat pattern. Unflatten. We still don't have the default. So I'll save this as Art Deco number 10. And so, again, I can look at that flat pattern out of the part, but really it's when I come over, we pick out of the view palette or from the model, I bring in that flat pattern, we go ahead and save it. Now when I come back, I have the expanded out, I have the default. And to me, this is what I want to see because this is what's going into the drawing. If there's an issue, if there's downstream errors, this is where I'm going to check. Flattening, it goes ahead and it does the flatten. It does pretty much the same thing. But once I have this derived configuration, see if I flatten that, it doesn't necessarily jump over to what the drawing is reading. So I'm not sure what prompted that that change in technique or change in strategy, getting the information over to the drawing. But out of the two, I probably don't use this near as much as I go into the configuration and pick that drive configuration. So check it out, see what you think, and we'll kind of go from there.